Welcome to The Explainer. I am so incredibly pumped you're here today because we have the absolute privilege of unpacking what is, without a doubt, one of the most vital, truly world-changing engineering breakthroughs in all of medical history. Seriously, we're going to look at exactly how humanity figured out a way to literally look inside ourselves without ever picking up a scalpel. Okay, let's dive into this. On the surface, that question probably seems completely absurd, right? I mean, what could a purely theoretical math equation and the famous music label that recorded the Beatles possibly have in common with advanced neuroscience? Well, as we're going to solve together today, they are actually the two unlikely puzzle pieces that gave doctors the ultimate superpower, the ability to see inside the living human body. Section 1. The flat shadow problem. You see, for centuries, doctors mostly just had to guess what was happening beneath the skin. Now, the standard X-ray was a huge breakthrough, for sure, but it had a massive limitation. It essentially acts like a flashlight shining against a wall. The result you get is just a flat two-dimensional shadow. Because X-rays compress a 3D body onto a flat 2D sheet, everything, bone, muscle, organs, it all just overlaps. And the most frustrating part of that limitation, soft tissues like the brain were almost entirely invisible. So finding a brain tumor back then often literally meant physically opening up a patient's skull.
Section 2. Two geniuses, one idea.
Now, the solution to this overlapping shadow problem didn't actually come from some massive, well-funded medical institution. It started with Allan Cormack. He was this brilliant South African physicist working in the US. Back in the early 1960s, Cormack started wondering, if you send X-rays through a solid object from a whole bunch of different angles, and then you measure the energy that comes out the other side, could you calculate exactly what is inside? So he crunched the numbers, and he actually proved it mathematically. But incredibly, his brilliance was largely just ignored by the medical world at the time. Enter our second unlikely hero, Godfrey Hounsfield. He was a British engineer working for EMI. And yes, that is the exact same company that was raking in cash as the Beatles record label. Now, Hounsfield didn't even have a university degree, but the guy was an absolute genius at building things. He independently had the exact same realization as Cormack, but instead of just theorizing about it, Hounsfield used his lab to actually build the thing. So in this small lab in London, Hounsfield builds a very primitive version of the machine. In 1971, they finally tested on a real patient, a woman with a suspected brain tumor. They scanned her head, but, they didn't just get an image right away. It actually took the massive computer of the time 2.5 hours to process just one single picture. But when that image finally appeared, wow, it was undeniably clear. They could see the tumor perfectly. For the very first time in human history, doctors were looking inside a living brain, zero surgery required. So the crucial point is they named this new machine computed tomography. Tomography actually comes from Greek words that mean to write a slice. And that Greek definition perfectly captures the brilliant physical mechanics of exactly what this invention actually does. Section 3. Slicing the loaf. Okay, let's break open the black box here and look at exactly how it eliminates those frustrating overlapping shadows. I want you to think of the human body kind of like a loaf of bread. A standard X-ray, it basically tries to look through the entire loaf all at once, which squishes everything into one flat shadow. But a CT scan does something incredibly smart. It looks at just one single thin slice of bread at a time, isolating a specific cross-section where absolutely nothing can overlap. Let's move to and see how this builds logically in the real world. First off, a patient lies on a table that slides into a large donut-shaped machine. Hidden inside that donut is an X-ray tube spinning around the body at super high speeds, shooting a really thin beam. Directly opposite that tube are sensitive detectors that are constantly measuring how much of the beam actually makes it through the body. And the machine repeats this process, capturing measurements from every angle in a full 360-degree circle, thousands of times per second. Now the machine translates those beams into hard data based on something called the Hounsfield scale, because as it turns out, different materials block different amounts of energy. For example, the air in your lungs blocks almost nothing, giving it a score of -1,000. Dense bone blocks a lot, hitting +1,000. And then soft tissues, like brain matter or blood, sit right in the middle, right around 0. But right now, we just have a massive pile of raw numbers. And this is exactly where Allan Cormack's work from the 1960s comes rushing back into our story. A powerful computer takes those thousands of measurements from all those different angles and uses that exact same mathematical formula Cormack came up with to reconstruct the slice. The math figures out exactly which Hounsfield number should be placed at every tiny microscopic point in that cross-section. And once that perfect non-overlapping slice is calculated, the magic just keeps going. The patient table moves forward by literally just 1 millimeter, and the spinning machine captures the very next sequential slice, and then the next, and the next. Finally, the computer rapidly stacks all of those individual slices together. The result? A complete, fully explorable, three-dimensional model of your insides that a doctor can freely rotate, virtually slice open, and examine right there on a screen.
Section 4. A modern medical revolution.
While that 1971 machine was an absolute triumph, modern scanners are truly just awe-inspiring. Remember that first brain scan we talked about that took 2.5 hours for one blurry slice? Yeah, today, scanners spin up to 4 times per second. What used to take hours now takes less than 10 seconds to scan your entire head, chest, or abdomen in stunning, high-definition clarity.
And this brilliantly illustrates how doctors have learned to push this high-definition clarity even further, using something called contrast. This is a special iodine-based liquid that's injected before a scan. Because it blocks X-rays, it shows up bright white on the image. It perfectly maps out your blood vessels, making it incredibly easy to spot a blood clot or even a hidden tumor that's growing its own chaotic blood supply. Because it is so unimaginably fast and detailed, the CT scan has truly become the ultimate emergency room superpower. When every single second counts, it can instantly find internal bleeding from a car accident. It can show a doctor exactly if and where a patient is having a stroke in their brain. It reliably detects tiny lung cancers, kidney stones, hidden infections, and complex heart problems. It is, absolutely without a doubt, one of the most critical, life-saving tools in fast-paced modern medicine today. The whole journey of this technology is just an incredible testament to human ingenuity. I mean, in the 1960s, it was literally nothing more than Allan Cormack's ignored mathematical proof. By 1971, Godfrey Hounsfield turned it into a working machine in a small English lab. And in 1979, the world finally recognized the sheer magnitude of what they had done. Cormack and Hounsfield, these two men who had approached the exact same problem from totally different disciplines, jointly shared the Nobel Prize in medicine for their invention. They taught a computer how to see inside the human body. And by combining math, engineering, and oddly enough, a bit of record company funding, they entirely eliminated the medical guesswork of the past. It leaves us with a fascinating final thought to ponder as we close out this explainer. If we can solve the impossible shadow problem with just spinning X-rays and math, what other impossible medical mysteries might our next generation of engineers and physicists solve next?